NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello and welcome. Good evening. Thanks. Well, welcome to NASA's Jet Propulsion Laboratory here in Pasadena, California. I'm Preston Dykes. Welcome to our monthly lecture and discussion series that we call the Von Karman Lecture. Our show this month is a Mars Roundup. Our two speakers will tell you about the activities of our Mars rovers on the Red Planet, including the next rover planned to launch in 2020, and the latest arrival on the Red Planet, NASA's InSight lander. Our first speaker is Dr. Abigail Fraeman. She's a research scientist working here at JPL, and her work focuses on understanding the evolution of rocky bodies in the solar system. She is the deputy project scientist on the Opportunity rover and was the campaign lead during the Curiosity rover's exploration of Rubin Ridge recently. Dr. Fraeman received her PhD in Earth and Planetary Sciences at Washington University in St. Louis and completed a postdoc at Caltech before coming to JPL in 2016. So please welcome Dr. Fraeman.
Awesome, thank you so much, and I'm so excited to see you guys all here today. What a good crowd. Awesome, so all right, let's get into it. I'll be doing the first half of this talk about our Red Planet Rovers and Insights, and I will be focusing on the rovers that we have currently exploring the planet and the rovers that we have headed to the planet. To start, I'm gonna take you back about 6 months ago from today. It was a Monday morning, and for the Opportunity rover, we came in the morning, and we were starting our regular tactical planning, as we do every morning for both rovers that are operating on Mars. We were parked at this interesting outcrop called La Jolla. That's an informal name for this rock, and we were investigating it with our instruments on the end of the rover arm. And if you take a look at the documentarian report, this is a report we have that we've done every single day we've planned this mission. You can see it reads that Opportunity is at the tan bedrock target La Jolla in Perseverance Valley, and the APXS, that's one of our instruments, is down. However, a dust storm is our next challenge. A measure of dust level that we call tau has jumped from 0.6 to 1.5. Why did we report this? Why do we care about what the dust level in the atmosphere is? Well, here's a picture of the Opportunity rover, and as I'm sure most of you in the audience know, the vehicle is powered by solar energy. We have solar panels on top of the rover that give us our power to charge our battery and do our science. When you have dust in the atmosphere, you can block out some of the sunlight, and so it makes it harder to get power onto these panels and harder to get power to do science. That Monday, when we had a dust level of 1, a tau of 1, the sun looked something like this. So we were interested. The sun was dimmer than it usually is, but we were approaching summer in the time of year where Opportunity was investigating. And sometimes we get dust storms in the summer. And sometimes they're kind of big. Sometimes we get regional level dust storms. And so we thought, you know, maybe this is a regional level dust storm. We're going to have a little bit less power for the next few weeks, but we're going to manage our power smartly. We've survived dust storms before. And so this is something to be wary of, but not necessarily something that we think is super horrible. The next day, on Tuesday, when we got the reading of what the dust measurement of, it had jumped even further. The storm had grown. The dust level was down to about 3 now, or up to about 3, and the sun was slightly fainter. By Friday, we'd realized that this was a pretty massive storm, and it was probably going to be pretty bad and probably one of the worst we've ever seen. We got data. We couldn't even tell how dark the sky was, because when we tried to take a picture of the sun, we couldn't see it through our solar filter. But we think the tau value, the dust level value, was something around 6. So this is a simulation of what the sun would look like when it was about 5. So this is now Friday. At this point, we know this is a very serious event. We could see from the orbital data that the dust storm was expanding. It was continuing to grow. We knew it was likely to become global. And so all we could do was hunker down, do our best to manage power over the weekend, and wait. So that's what we did. We were very careful. We canceled some of the downlinks we thought we were going to have in an attempt to save power. And we sat and we waited. So we're waiting the downlink on Sunday. That's when it was supposed to come in. This is what a sun would look like if a tau level was 7. This is what it would look like if a tau level was 9. This is what we saw when we got the downlink on Sunday. We had a tau level that was above 10.5. So the sun probably looked something like this to the vehicle. This is the highest we've ever measured on the surface of Mars for how dark the sky got. We honestly were amazed that we heard from the vehicle at all, but we knew at this point we were probably going to lose contact with the vehicle. It was probably going to slip into what we call a low power mode fault, and the only thing we could do was to sit, hunker down, and wait it out and see what happened. But let's go back a little bit, and let's talk about what Opportunity was doing before this all happened, and the really interesting science that we were doing. You know, why was our arm down on that particular rock? Well, Opportunity is our robot field geologist on the surface of Mars. The payload of the rover are instruments that are designed to act like a geologist in the field would do. We have a tool that we can use to grind into rocks that's a lot like a rock hammer. We have a microscope that acts like a geologist's hand lens. We can look up really close to the rock. And we have other instruments that we can use to measure the chemistry of the rocks and get really fine-scale pictures of them. So integrated, we can use all of these tools to tell us about the geology of the environment and to understand the past and the past processes that form these rocks and shape these rocks. Throughout its traverse, Opportunity has started up here at Endurance Crater, and we've crater hopped through the plains of an area called Meridiani Planum. We started in Endurance, we traveled to Eagle Crater, then we traveled down to a slightly bigger crater called Victoria Crater, and in about 2010, we got to the rim of this giant crater. It's about 22 kilometers in diameter, called Endeavour Crater. And this crater is a really exciting place for us to study because we know that the rocks exposed in the rim of this really large crater are a lot older than the plains rocks that we'd been driving across. So they represent a period of time in Mars's history that was a lot longer ago than the rocks we'd been looking at before. So we got to see different environments, different kinds of geologic processes. All of their signatures were in these rocks. The mission basically started over again when we got to the rim of Endeavour Crater. This is also the first time we've been able to investigate the rim of such a large crater on any planet anywhere. And that's really important because impact processes, the formation of crater, is a universal process across planets in the solar system. So the opportunity to investigate one on another planet to get really good data is important, not only for understanding Mars and its history, but also how does this process operate across the entire solar system. For the past year, we've been exploring this feature called Perseverance Valley, which is about the size of a football field. And this is an area on the rim of the crater. You'll note here the north arrow is pointed to the side. This is just to kind of show what it looks like. We're driving down the valley into the inside of the crater. And what's really neat is from orbit, this valley looks quite interesting. You know, we kind of see these bifurcated channels, almost these flow features. So the question we were really interested in answering is what were the processes that formed this particular valley? Now, we had three kind of ideas that we thought of before we went into the valley. The first was that it formed by a dry avalanche. So you just had a bunch of rocks that rolled down the hill and carved this out. We didn't think that was likely because it was a little too shallow. The second idea was a debris flow, which you can have on slightly shallower slopes. And in this case, it would be kind of a slurry of mud and rocks. Or the third option, maybe this is an ancient river channel. This is kind of a gully that was a lot of water. So we went down there and we used our instruments to check this out, see if we could figure it out. This is what the valley looks like, kind of at the top looking down. And you guys might look at that and say, where is it? I don't see it. And it turns out the morphology, it's really subtle. You know, this is a really subtle feature that gets really well emphasized when we see it from orbit. But this is a beautiful view. We're looking down. You can kind of see a shadow. That's our mast right there. But when we got in the valley, we did notice something really interesting, and we started looking at the rocks that were exposed there. And what we found was evidence that there's these linear faults that were kind of running up and down the valley. You can see there's two kinds of rocks on either side of this fault. So there's a process here that's shaping the faulting, these linear radial faultings along the crater rim. And then when we took a closer look at some of the rocks on them, we could see that they were sculpted in a really interesting way. And if you take a really close look, you can see in this rock, there's kind of these more resistant little pebbles sticking up. And then coming off of these pebbles are these sort of flow lines. So you go, flow lines, maybe this is evidence, here's our river. But when you look carefully at the direction, they're pointed uphill. And water doesn't flow uphill. So this isn't water that's shaping these, at least modern day surfaces. This is wind. This is the result of wind erosion in the modern day surface of Mars. So integrating all of these things that we found, we came up with a new hypothesis to consider. Maybe parts of this valley are carved by wind erosion. We have these faults that we see cutting through them. Maybe wind is taking advantage of these pre-existing faults and sort of carving it out. But if they were partially a debris flow or a river, we might expect to find all of these deposits that would be carried by these events that would kind of be the signature for these events. They'd be at the bottom of the valley. So we have to wait till we get to the bottom of the valley before we can really say for sure, are these deposits here or aren't they here? So we're still exploring. Another awesome thing that Perseverance Valley exposed that was totally unexpected were some really interesting rocks. And the rocks that it turned up are unlike any of the rocks that we've seen before in the entire 14 years of the mission. It was something completely new. Here's a picture of some of these rocks that this big valley was sort of digging up, and you can see their textures. They have kind of pits in them. So we're wondering, is this a weathering? You can weather rocks and get pits that look like this. They could be from trapped gases that were in the rocks that are coming out. We're not sure. And so we were investigating the chemistry, the textures of these rocks, and that outcrop that we were on when the dust storm hit, that La Jolla outcrop, that was one of the rocks that was nearby to these rocks. And what we were trying to do was figure out, how does the composition of these rocks differ from the rocks that are surrounding it? Is there some sort of relationship in terms of, maybe one melted from another or not? So we were trying to piece together this whole story. And that's why we were at La Jolla, and that's what we were doing when this day in June happened and we lost contact with the vehicle. We did something else really fun in Perseverance Valley, and that was we hit Sol 5000 of the mission. That's a pretty big number, Sol 5000, and we wanted to celebrate it. And so we did a first-time activity that we had never done for 14 years, and that was take a selfie. Now, you've probably seen the selfies from Curiosity, and Curiosity takes those by taking the camera on the end of its arm, and they look really good, and we were kind of jealous. And we said, we have a camera at the end of our arm, and yeah, the focus is not quite the same, so if we take a selfie, it'll be a little blurry, but we can do it. And some very smart people put their heads together, they planned this mosaic, and I think it came out beautifully. And so this was awesome, because this is the first time human eyes had seen this side of opportunity since it's left Earth in 2003. So I'm so glad we got this observation, and it's really special to commemorate Sol 5000. And I'm going to put that into context to you. How long is 5,000 sols? So here is my personal career plotted along Opportunity's traverse. And Opportunity is a very special rover to me, because when I was in high school, I actually got to come out to JPL as an outreach program sponsored by the Planetary Society and be here the night that Opportunity landed. I got to be in this room for the landing press conference. I got to be with the science team, and that totally blew my mind. It inspired me to pursue space exploration. And so I took that night and I said, this is great. This mission will last 3 months, maybe 6, and there'll hopefully be more stuff going on. But since that time, I managed to graduate from high school. I went to undergrad, graduated from undergrad. I started grad school. My graduate advisor is on the Opportunity Science team. So as a graduate student, I started doing tactical shifts. I was a documentarian, so I got to write those reports that I read you at the beginning of the talk. Finished grad school, went on, started a postdoc, finished my postdoc, came here, and now I'm the deputy project scientist of the mission. So this mission has been going a really, really long time. We do know we haven't heard from Opportunity. It's been exactly 6 months to today, because June 10th was the last time we heard from it. It's now January 10th, so 6 months today was the last time we heard from it. We do know it's still there. This is a picture we captured from orbit after the dust settled, and we could still see the surface. Can you see the rover in Perseverance Valley? There she is. So we can see from orbit she hasn't blown away. And so what we're doing now at JPL is we're trying to do these recovery efforts for the vehicle. So we think the temperatures haven't gotten cold enough that anything would break. We're in summertime, so that's helpful. And so what we're trying to do is two things. First, we're gonna always be listening for the vehicle. So if everything if she wakes up, if whatever dust has settled on her solar panels that is causing her to have low power blows away, we'll hear from her no matter what. If there's just enough dust to blow away that she can wake up, but she doesn't have quite enough power to call home, what we're doing is a campaign of what we're calling sweep and beeps, where we're sweeping the frequency ranges that we know that she's listening, and we're telling her, beep if you hear us, beep if you hear us. And so we've been doing that campaign for a few months now, and we're just waiting, and we're hoping that there'll be a beautiful gust of wind that'll clean the panels off, and we'll hear from her. This is what the dust storm looked like from orbit. You can see it started right around Opportunity, but you'll notice there's another guy on the planet, Curiosity. That's the other rover. And this event was so big, it encircled the planet, and Curiosity saw it as well. So take a look. This is June 11th. That's what the storm looked like. Here's one of those selfies that we took with Curiosity on June 15th. This was right after. It was a great week for Curiosity that week. We used our drill again. We collected a drill sample after a very long time. We hadn't been drilling, but we got our drill up. We got this Duluth drill sample. But you can see in the selfie, there's sort of this ominous dust cloud on the horizon as this global dust storm is approaching. And this is an series of images we took of the wall. We've landed in a big crater with Curiosity, and we can watch as the mountains on the wall in the crater get harder and harder to see. It's kind of like a smoggy day in LA when the smog comes in and you can't see the mountains anymore. That's what we're seeing here. So, the dust storm was really bad for Opportunity, but it's a great chance for Curiosity to, for the first time since Viking in the 70s, we were able to make observations on the ground of a dust storm and the effects it has on Mars. And this is really important because it helps us understand more about how these processes start, how they operate, and the effects that they have on the surface. Curiosity is fortunately equipped not only with the cameras that you can see, but we also have a weather station on Curiosity. So we can make near continuous measurements of how the dust storm affected the temperature, how it affected the pressure, how it affected relative humidity, the UV radiation reaching the surface, all of these wonderful things that we can now put into our meteorological models and better understand how these events happen and evolve. This is one of my favorite pictures. This is that Duluth drill hole. This is what it looks like kind of in a normal day. You can see here's the rock, here's some sand nearby. This is what it looked like at the height of the dust storm. Every picture we took in the height of the dust storm has this kind of unearthly, really reddish hue. The exposure for this picture is also a lot longer. So you can think of it's really, really dark. Turns out we had to expose the photos a lot longer for Curiosity, and we had to build that into our margins for our planning, that the photos were going to take longer when this dust storm was happening. But everything kind of looked this really cool, weird red color. But we got a lot of really good observations about the environment and what was happening. In September, after the dust storm settled, these storms can take weeks to kind of settle out of the atmosphere. It turned out there was a lot of dust that settled on the vehicle. So this is a picture of one of our calibration targets for a microscope, and it's kind of a play on the geologist's penny for scale. So we have a penny for scale on the rover, and that's what the penny looked like. And this is in September. So right when the dust storm had finished, all the dust settled out onto the rover, and Curiosity was pretty dusty. But turns out Gale Crater is a pretty windy place. And by December, when we imaged that exact same spot, it's totally clean. So just the regular seasonal winds have cleaned off Curiosity. What does this mean for Opportunity? Well, it's hard to say. It's like trying to predict the weather in London if you're in New Zealand. We're opposite sides of the planet. But it's a pretty cool effect of just how mobile this dust is in this modern day Martian environment. So here's what Curiosity looks like. And if Opportunity is our mobile geologist, well, Curiosity is a mobile chemist. And part of the reason that Curiosity is such an exciting mission is because it has two very special instruments inside the rover that can make kind of really advanced measurements. And to make those measurements, we need to get samples of rocks that we've drilled inside the rover. We've spent the last about year or so exploring this ridge that's part of this mountain that we're climbing, this Mount Sharp. Here's a picture of the ridge. We can see kind of climbing up. We're on the side of the picture, so it's tilted a little bit, but you can see it's this ridge. And this feature we've named Rubin Ridge. And we've named this after the astronomer Vera Rubin. She's a remarkable woman, and her most well-known discovery was that she was the one who made the observations that led to the discovery, and she discovered dark matter. So this mysterious force that is in everything, and we don't know what it is. And she was the one who made the very precise rotational curve measurements of galaxies. On this mission, we name major features after scientists. We have Murray Buttes after Bruce Murray. We have the Bagnold Dunes after Ralph Bagnold. And to me, personally, it was very exciting to be able to choose a really prominent female scientist to name this after. I'm really happy that we're on Vera Rubin Ridge, and I'm really happy with this name. Another little fun fact, she has several children who are all scientists as well, and one of her sons, David Rubin, is actually a member of the Curiosity Science team. So it was easy to find the family to contact to get their permission, because one of their family members was on our team. This is what Vera Rubin Ridge looks like from orbit. So you can think of the ridge, it's kind of this Tanner-looking feature that's kind of wavy like this. This white line is Curiosity's traverse. And you can see kind of the biggest thing is just in this picture, the ridge looks pretty different from the rocks below. So before we got here, we were really curious. You know, we knew these rocks were lake bed deposits. What were the rocks in the ridge? And then also, from orbit, we've mapped this mineral called hematite, which is a mineral that forms in water. And what's really exciting is the reaction that forms hematite can be favorable to life. And we saw this from orbit, and we saw it just light up along the ridge. And so we were really interested in what was causing this. And I'll say on a personal note, one of the chapters in my PhD thesis was the discovery and mapping of this mineral with the orbital data. So I'm super excited to be able to get to this ridge, to drill, to see what we find. And then it's also a little bit scary because it's one of the few times in planetary science where what you predict you see from orbital data can actually be tested by kind of the definitive on-the-ground instruments. So I had my fingers crossed that we'd find this mineral that I said we'd found and hopefully figure it out. So, you know, we get there, we drive around, we drive right to the spot where we have the strongest signature, and this was, you know, I said, we have to go here. This is what we see from orbit. This is where we need to go. And, you know, crossed my fingers. We got our drill sample. I wanted to see what was in it. We picked the rock. Oh, excuse me. This is what the rocks in the ridge look like. We found, first of all, we found that they were layered rocks. They're these beautiful, beautiful layered rocks. And we decided that these rocks are very similar to the rocks below. And these were probably also formed in a lake similar to the rocks below. But getting back to the story of the drill, because I'm really excited, because I really wanted to know. I'd been waiting for 5 years since I graduated from grad school to know if this mineral was really there. We went to drill, and that's what happened. And what happened was the rock was too hard. And the vehicle sensed that the rate that the drill was making progress was basically 0. And we stopped drilling because we couldn't get through the rocks. You know, I guess this makes sense. We're sitting on this ridge. It's a ridge because it's harder than the rocks around it. And the rocks are really hard. So it was a little disappointing, but you know, we're engineers, we're scientists. Let's try again. Let's pick another rock. And so we did. And this rock was too hard. And it turns out a lot of the rocks here were just so hard. So Mars threw a challenge at us, and it was really disappointing because, you know, in particular, this was the drill sample. Of all the drill samples in the mission, I really wanted to see what was in this drill sample. So it's a challenge. We put on our engineering hats, we put on our geologist hats, and this was actually, I think, a really cool part of the mission where the science team and the engineering team really, really worked together to solve this problem. So the engineers went and they looked at, you know, what can we do to make the drill slightly more powerful, slightly more able to penetrate these rocks. And then on the geology side, we said, okay, what can we do to try and find a rock that might be a little bit softer and might be more able to drill? And so, you know, you look at a rock like this, how do you know if this is going to be drillable versus those other rocks? And we came up with 3 things to look for. First, we came up with, you know, let's just look for the broad scale topography. If the rock is slightly lower, maybe it's a little softer, more easily eroded. We looked at the way the rock was weathering with respect to these white veins that are cutting through. You know, if the veins were standing up with respect to the rest of the rock, maybe the rock was soft. If the veins were recessed into the rock, maybe the rock was hard. And then also, we have a brush that we have on Curiosity. And it turns out if you look real closely at where you can brush, sometimes you can see scratches in the rocks, and sometimes you can't. But the rocks we see scratches on, we see that they're maybe a little bit more easier to drill. So we kind of put on our geology hats. We looked at a lot of pictures that we'd taken of the rocks. We picked this rock. We said, you know, we feel pretty good about this one, and if it's not this one, we don't know what we're going to be able to find. And we crossed our fingers. We waited for the data, and then we got a full drill hole. So this is my favorite drill. We have 19 drill holes with Curiosity right now. This one is my favorite, hands down, because I didn't know if we were going to get it, and I was so excited to get it. And we got it. We analyzed it. It turned out, yes, the mineral hematite, it's there. It's the most that we've seen at any drill hole, although not a huge amount. But the orbital detection is correct, and we're kind of looking at now the bigger picture to understand, okay, what does this mean about the past habitability of Gale Crater? We've gotten 2 more holes on the ridge since then. We've gotten this really interesting gray one, and then this one we got right before Christmas. And this is what we're doing right now. We're sitting in front of this high field drill sample, and we're analyzing it to figure out what it's made of. We found some cool stuff, and yeah, so we have 3 drill holes now from the ridge, and one very happy person on the team. Many very happy people on the team, but for myself, I'm very happy. And it's been a great campaign. But what's next? So next, we're going to keep climbing this mountain, and we're going to head into these rocks further up the mountain, which are just beautiful to look at. I can't wait. I love the ridge, but I'm ready to get off it and go to new, really exciting places. So in particular, these kind of purpley-looking rocks, these rocks we see from orbit have a signature of clay minerals, and those are really interesting because they have the potential to really well preserve organic molecules. And then beyond that, we see all these color changes, different rocks, different environments that we're going to get to explore as we drive up through time up this mountain. I'll leave you talking about the last rover, which is this rover that we're launching in 2020, which is creatively named Mars 2020. It will get a new name, but if Opportunity is our geologist, if Curiosity is our chemist, Mars 2020 is our little collection rover. And really the big science that this rover is going to do is it's going to drive around and it's going to collect little rock samples, and it's going to collect these rock cores, these little kind of chalk-sized cores, and bring them back to Earth so we can analyze them in our laboratory. And this is really going to revolutionize, I'm sure, our understanding of Mars. We just announced we picked a landing site. Mars has a lot of really exciting places, but we're looking forward to landing in this place called Jezero Crater. We're going to land somewhere in this yellow circle, this ellipse. And Jezero Crater, this is the rim of the crater. It's exciting because leading into it, we see this feature, which is actually an ancient delta. So we know that there was a river coming into this crater. This crater was filled with a lake, and there was a delta that was feeding into these really calm waters forming this shape. We can also see the minerals in this delta are what you would expect to have formed in this really kind of quiescent environment, and a really exciting environment if you're looking for a place that may have preserved signs of past life. So stay tuned for more from Jezero. And I'll leave you with really the latest and greatest. These are pictures that we took just in a building down the road here at JPL of the current state of build for this rover. These were taken a week or 2 ago. This is what the clean room looks like. We build everything in a clean room to make sure we don't get little gunk and particles to clog the electronics. But if you look closely, you'll see these guys. These are going to turn into the back shell and the cruise stage. This guy back there in the corner, blown up there, that's going to be the sky crane. Those are going to be the thrusters that's going to help the vehicle land. And then I think most excitingly, that little kind of innocuous box that's all wrapped up back there, well, that's actually the chassis for the vehicle. So we're starting construction on this and really looking forward to launching and getting our samples and bringing back to Earth. So that's all I have for you guys talking about rovers, and I think our next speaker will talk to you all about our most recent neighbor and lander.
Pretty cool stuff. Thank you so much, Abby. All right, well, it's time for some insight from our next speaker. Elizabeth Barrett is a science systems engineer at JPL working on the Mars InSight mission. In this role, she coordinates with the science and instrument operations team to accomplish the mission's goals. Dr. Barrett received a Master's of Engineering from Cornell University, taught English in post-war Bosnia for 18 months, and then returned to school to receive a PhD in astronomy from the University of Hawaii. After that, she worked for 8 years as a flight controller for the International Space Station before joining JPL in the InSight mission in 2015. Please welcome Dr. Barrett.
All right, thank you guys for coming. So as Abigail mentioned, InSight is our newest addition to Mars, and the biggest difference you can see, no wheels. So we're a lander, we stay in one place. InSight is very different from the other missions. The other missions are investigating the surface of Mars. They've done a great job analyzing the surface of Mars. InSight's looking at the interior of Mars. So InSight's a geophysical station, and we're going to use seismology, heat flow, and actually measuring the wobble of Mars as it rotates to determine the interior structure of Mars. What does the core look like? What does the crust? What does the mantle look like? We've been able to do that for Earth, of course, and we've also been able to do that for the Moon. But we've never been able to do it for the other rocky planets. So we're very much looking forward to Mars as an intermediary between the size of the Earth and the size of the Moon to show us the different types of terrestrial planet evolution. Where did InSights begin? So it launched on Cinco de Mayo from Vandenberg Air Force Base here on the West Coast. First interplanetary launch from the West Coast. It launched about 4:05 a.m., and it was a beautiful launch, as long as you were not at the public viewing site. If you were there, you saw something kind of like that. It was very dense fog. A lot of people have described it as the best launch they ever heard. But at least we launched. After that, we began a 6-month journey to Mars. So it took us 6 months to get there with about 6 little trajectory correction maneuvers along the way to make sure we landed at the exact right spot on Mars. And then on Cyber Monday, that's the 26th of November, right after Thanksgiving. We got a great Thanksgiving present, and just before noon, InSight successfully landed on Mars. And so we were all very excited. You can see even in the engineers in the control room, our project managers and PIs celebrating. I was lucky enough to be able to spend that time with the scientists and the instrument engineers. And as soon as that first picture came down from Mars, they immediately crowded around and were looking at where they could put the instruments on the surface and trying to analyze how many rocks they could see, immediately getting to work, even in the room where we're still watching the landing. All right, and then of course, no story of InSight's landing on Mars is complete without thanking our Marco companions. We had 2 little cube satellites that went to Mars with us. It was a technology demonstration to have the first CubeSats go interplanetary. They were able to provide relay data for us during landing so that we did not all have to hold our breath during landing and wait to see if we got a beat from the surface of Mars. Instead, with they relaying the telemetry to Earth for us, we got to watch a near continuous stream of telemetry and hear updates along the way for landing so we could breathe a little bit better. So Marco is now continuing on his way around the sun, and they were very helpful in getting us to Mars. So, okay, where did we land? Well, we landed on Mars. It's a good start. You land on the wrong planet, it looks really bad. We're about 375 miles, or about 600 kilometers north of Curiosity. That's the big rover that Abigail was able to talk about. So we're sharing that same general area, but we're in a slightly different location. If we zoom in a little bit on that landing site, this is our landing ellipse where we intended to land. And those navigators and landing team people can do their job pretty well because we landed right there in the ellipse. You zoom in a little bit closer, and Mars Reconnaissance Orbiter, one of the orbiters around Mars, used their HiRISE instrument to get detailed images of where InSight has landed. So the big image is actually a pre-landing image, just showing you the relative location of the different items. The heat shield landed up north and by that big crater. The parachute and back shell landed down south, and if you actually look closely at the parachute image, you can see the deflated parachute lying on the surface of Mars. And then the lander was right there in the center, and you can see that we even created a little blast zone around us as our thrusters came down for landing, blowing off that loose, dusty material from the surface of Mars. Well, what did we do after landing? Well, actually 30 minutes after landing, we had to deploy our solar array so we could generate power to continue with the mission. We did it about 30 minutes after landing, but unfortunately, due to the way the missions work, we couldn't get confirmation of that deployment until about 5 hours after landing. So that first landing day was a little bit tense until we heard that those solar arrays were successfully deployed, and then we could all go to happy hour and celebrate a little bit. So we have great solar array panels. I think they look a little bit like Mickey Mouse ears, but. After that, we checked out the instruments. First thing, they're still attached. That was a good start. We powered them all on for about 15 minutes to make sure that they were working okay, and you've never seen happier scientists than the first 15 minutes of data that they got. They analyzed that for days, just those 15 minutes of data. All right, after that, we then did a lot of surveying of our workspace out in front of us. So if you see the public images coming down from InSight, there's a long stretch of time where you're like, wow, they really like taking pictures of dirt. We were taking pictures of our workspace here to get a very detailed stereo image of what it looked like in front of our lander. And the amazing thing is, very few rocks. We couldn't have been happier. We had to decide then where to deploy our instruments. And this little purple bluish outline shows where we can put the images, or the instruments, the reach of the arm, trying to deploy those instruments out. And even more fun, this little area right here, you zoom in, and there's a little bitty rock there that as we came down for landing, you can see the divots along the ground, and it seems to have rolled along the ground with those thrusters pushing it. So of course, the scientists called it the rolling rock, because rolling stone is taken. So what are these instruments that we're going to deploy? Well, one of them is our seismometer that we called SEIS. It's going to listen to the seismic waves to investigate the interior of Mars. How are those seismic waves generated? They can be generated by Mars quakes, not earthquakes. They can be generated by meteorites striking the surface. And it's so sensitive that if you convert the acceleration that it can detect into actually a deflection distance, it can actually measure movement smaller than the radius of a hydrogen atom. So it is a very sensitive instrument. WTS is our wind and thermal shield. That goes on top of SEIS to protect it from the environment, to protect it from the thermal variations, to protect it from the wind, because the seismometer is so sensitive, you don't want to detect just the wind rattling it. You actually want to protect it from that. Another instrument we have is called HP Cubed. It's our heat flow measurement probe. It has a self-penetrating mole, looks like a little nail, that buries itself under the ground up to 5 meters, or about 16 feet deep. It contains, the tether it drags behind it contains temperature sensors that can measure the heat flow coming out of Mars. It also has a radiometer that's attached to the back of InSight on the deck and can be used to measure the temperature of the ground using the radiometer. So this one's going to detect heat coming out of the planet. We also have another set of instruments that were designed particularly to help our seismometer to understand the noise that it's seeing, but also can be used to do stealth science. So we have an environmental sensor suite. We call it the Auxiliary Payload Sensor Suite, or APSS for short. One of them is the pressure sensor, and you can see the little inlet for the pressure sensor here on the deck. The sensor's buried in the depth of the lander. We have twins, which measure wind speed, direction, and temperature. They look like little fingers sticking out in the wind, either way. Then you have IFG, which is our magnetometer, measuring the magnetic field, in particular to make sure that we understand magnetic fields that's generated by the lander and how it could affect the seismometer, but it can also measure the local magnetic field, of which Mars has very little, but we're still going to measure it. And then we have another experiment that we can do, but it doesn't take its own instrument, because it's going to use the medium gain antenna that we already have to talk to Earth, these two little cones on either side. And by measuring the change in the little signals as Mars is rotating around, we can actually track accurately up to 10 centimeters the location of InSight and how it's wobbling around, and thus how Mars is wobbling as it rotates. And just like you spin an egg, and hard-boiled egg spins different than a non-hard-boiled egg, that's what RISE is going to help us measure to determine what's inside of Mars. We also have something called Larry, which is on the backside of the deck. It's near our calibration target, and it's a laser retroreflector. So you can shoot a laser at it from a satellite orbiting in orbit, and it can get the reflection back to help accurately determine the location of InSight. That's an Italian Space Agency contribution. And then, of course, for everybody who submitted their names to go to Mars, we've got the chips with all your names on it also on the deck of the lander. So that's great. Where are our instruments? They're on the deck. Twins, you can see on either side, they're bolted to the deck. They stay there. The other instruments here located on the deck. But surface deployment is the key for InSight. The quality of a seismic station is directly related to the quality of installation. What does that mean? Well, in Viking 1 in 1976, we actually had a seismometer on the mission. You can see it there on the deck and not on the ground, so on the deck, above legs that were dampened and in a vehicle that could shake in the wind. So as a seismometer, it wasn't measuring the best data. Instead, the principal investigator for this mission says one of his big contributions was saying, well, I have an idea, put the seismometer on the ground, and then maybe we can get better data. So that's what InSight wants to do. Additionally, HP cubed is on the deck when we land, where it's supposed to be. But you don't want it there when you start hammering, because the engineers assure us that's not going to be a good idea. So you want to put that on the ground as well. But after we've traveled all the way to Mars, the instruments are still about a meter away from the ground. We need to get them on the ground. So how do we do that? Well, we want to get SEIS and WTS on the ground, and we want to get HP cubed on the ground. We use our robotic arm, or instrument deployment arm, to do that. And it has a little grapple hanging off of it that we use. So basically, we're playing an interplanetary claw game. Those little carnival claw games you can do. And in this case, unfortunately, if you mess up or you miss it, you can't put in a few more quarters and try again. So you got to go nice and slow to get it right the first time. To make it a little easier, we do provide a camera here called the deployment camera on the arm to look down the arm, and another one underneath the lander that looks out in front of the lander, the context camera. So it's not completely blind. Well, here, what have we done lately? At the end of the year, in December, we actually deployed SEIS to the surface of Mars. So it's now on the surface. That was so cool. We got to watch it again. There it goes, flying through the air, and it's safely on the surface of Mars. You'll notice the tether is still attached to the vehicle, and it kind of flutters in the wind a little bit. That's going to mess up our measurements of the seismometer. So the next thing we do is we drop the tether to the ground. If you missed it one more time, we let the tether go, and it falls to the ground. So that lets the tether slack out, and then we do a few more weeks of commissioning before we're going to move on. So what does the rest of deployment look like? Well, this is a simulation that was created before InSight landed. It's very accurate, except we have fewer rocks in our area that we're deploying the instruments, so we're even better off. So here you can see we're deploying SEIS to the surface of Mars, just like we did in December. Once SEIS is on the ground, as I said, we have several weeks of checkouts. We want to make sure it's level, that the instruments are performing correct, that we get as low as possible, that we've isolated the seismometer as completely as possible from the landing before we move on. After that, we go back to pick up the WTS, that's the wind and thermal shield again, and we're going to put that directly on top of the seismometer. So once we deploy WTS, we cannot physically interact with the seismometer anymore. That's why we take our time before going to this next step. WTS deployment is expected in mid-January, so it's coming up soon. You can see when we pick it up, it drops a little skirt. That allows it to have better contact with the ground when we put it over SEIS to protect SEIS better from the environment. Once WTS is on the ground and we confirm that there's no problems with SEIS underneath, then we're going to move on and go back to get HP cubed and deploy it to the surface. This simulation actually shows the instruments pretty closely to where we're deploying them on the surface of Mars. SEIS will go a little bit off to one side, HP cubed to the other. They want to be approximately a meter apart at the grapples so that they don't interfere with one another in a negative way. That way, the WTS shadow does not interfere with HP cube's measurement, and HP cubed hammering does not inadvertently trouble SEIS, even though we will use it for some cool measurements because we're generating a seismic signal. So once HP cubed is safely on the ground, then we make sure it's in a good location and release the mole to the surface so it can begin its penetration phase. So what does that look like? The mole hammering mechanism, it's like a long nail with a hammer inside of it, which saves time. So there's a motor here that's going to spin a weight and lift it up. As it lifts the weight, it's actually compressing a spring above it, and then the spring pushes that weight down really rapidly and hits the tip and moves it slightly into the ground with every stroke. So it slowly hammers its way in, and there's actually a spring at the top that absorbs some of the recoil so it doesn't just bounce in place. As we go down, we're going to go about 50 centimeters at a time and then pause, let the soil cool off for a few days, and then do a thermal conductivity measurement, and then move on. Because once we've left one depth, we cannot come back to it. It stays in the surface. Then we go all the way down for 3 to 5 meters, up to 16 feet beneath the ground, taking measurements as we go. Once we're there, we stay in that configuration for the rest of the mission. That's for 1 Mars year or 2 Earth years, and measure the heat flow coming out of the planet using the temperature sensors scattered along the science tether that we've dragged behind the mole for the rest of the mission, figuring out the heat coming out of Mars and therefore providing a constraint on the various models. This is where InSight is right now. We're looking forward very much to seeing WTS deployment coming up soon, middle of the month. We expect HP-Cube deployment end of January, early February, if everything goes smoothly, and then moving on to the hammering phase. And we're looking forward very much to the exciting science to come. So please follow InSight as you can as we go forward on Mars. Thank you.
Okay. Thanks so much, Liz. We're going to get set to take your questions now. If you'll come down to the microphone in the center aisle for your questions. And while we're getting set up, I'd like to show you a cool new online tool for getting to know more about the InSight mission. It's called Experience InSight, and it's a 3D interactive model of the InSight lander. You can rotate it in 3D, you can deploy the solar arrays and the instruments yourself, you can take control of the robotic arm to get a feel for how it works, and you can click around on the different spacecraft components to learn more about what they do. Experience InSight works on your computer as well as on your mobile devices. So check it out at eyes.nasa.gov/insight. Okay, and so if Abby and Liz will join me back up here, we'll get set for your questions. And it looks like we do have one.
Okay. Testing. All right, great. I had a question about the Mars 2020 rover. You mentioned that one of the exciting things about it is that's going to be taking rock samples and bringing them back to Earth. How is the return process going to happen?
Yes, that's a great question, and we're still kind of talking through details. We have a lot of options for possible ways to do it. Broadly, the architecture is probably going to look something like we're going to send another rover, a fetch rover, that's going to collect the samples. We're going to launch them, send a Mars Ascent Vehicle or a MAV to launch them back into orbit, and then some details about how it's going to orbit Mars, and then we'll pick it up, or we'll just send it directly back to Earth. But it'll be a multi-step process.
Okay, thank you.
Sure.
Oh, yeah, a couple of questions. Well, first of all, for the drilling problems you're having, is there a percussive element with a rotational element? In other words, like a hammer drill effect that you've used, and has that worked out, or what's the status with that?
Yeah, so the question is about the Curiosity drill. Yeah. And so the Curiosity drill, yes, it's a percussive drill, a rotary percussive drill. So that means it spins and it percusses both. We attempted to do a couple drills that I didn't show using rotary only and didn't get very far. But those drills that we tried with the rock was still too hard. That was rotary and percussive, kind of at our maximum percussion level. The drill has several percussion levels, and it has a smart sensor on it that it can figure out when it needs to kind of up the rotation or up the percussion. And so we kind of maxed it out at our level 5, and we still found we weren't making any progress.
And is there a way to use the actuators in the arm to assist in the percussion element? So you could have the arm pushing at alternating frequencies to aid the effectiveness of the percussion effect?
So yeah, I'm not sure. I don't. The arm itself. So how the drill used to work is it had these kind of prongs that would put down on the surface, and then we had a feed mechanism that actually extend, and so the arm would be completely stationary. The feed mechanism is no longer operating, so the engineers actually did some really amazing work figuring out how to operate the drill without the feed mechanism, so fully extended. So think of it kind of like using a drill how you would use it anyway, just kind of pushing straight down. So we have the weight of the arm that's kind of being the gravity vector. I don't think we'd be able to percuss the arm as fast as we percuss the drill. I don't know, as an engineer.
Seems like I wouldn't recommend it.
Yeah. Thought there might be some hazards associated with that. And I'm sure this one is something that's occurred to you, but I'm going to bring it up just to find out why it wasn't done. With the solar panels, I mean, everybody's thought of some sort of like a windshield wiper type effect. I've even heard of artificial muscles that could be used to have the action with very little energy requirement, or you could turn them on an angle and shake them or use air jets. Surely you must have come close to trying something. What did you think of, and why didn't you do it?
Well, I know when I came, I actually asked that question to somebody. I was like, why don't we have a windshield wiper that can just occasionally go across? And the answer is, as an engineering thing, that's another motor you have to heat. You've got to make sure it can work. There's a lot of items there where we know if you size the solar arrays big enough and if you get these occasional dust cleaning events, that we tend to be okay as we are now. So it just hasn't been a requirement at this point.
And just a reminder, the requirement for the Spirit and Opportunity was 90 sols. And it was easier to build bigger solar panels that would get you to 90 sols than it would be to try and find one of these devices that would add complexity. And it's just been a gift that they've lasted so long, and it's been a gift that we've had these cleaning events.
Well, with 2020 hindsight, which of course is very suspect, would you say after 6 months that maybe it might have been a good idea to try one of those mechanisms?
Absolutely not. I think that the way they are designed was perfect and beautiful, and I think that they've far exceeded what they were designed to do.
Okay.
Thanks for your question.
Hi, thanks for the presentation. Could you explain in a little more detail the mechanism behind the HP3 mole? Specifically, you've got a nail there that's, I don't know what that is, 8, 10, 12 inches, something like that?
It's about maybe 30 inches or so.
30, okay. And then,
sorry, 12 inches, about a foot long.
Okay, so like I said. And whatever material is attaching it to the instrument on the surface must be a softer, malleable material because it presumably is coiled up somehow inside the instrument?
It doesn't actually rotate at all. It just percusses its way down. So it won't actually rotate. It just pulls out the tether, and the tether's stored in the portion on the surface, and it gets pulled out as it goes deeper.
Right, that's what I'm saying. So you've got a tether that's
Yeah.
some kind of softer material that's
It is.
attached to the nail.
Yep.
And so how is it able to transmit the force as you get deeper and deeper into the ground through that softer material? That device that is
So
able to do that?
The device is actually in the nail itself. So it actually hammers
okay,
itself deeper
okay.
and just pulls the tether behind it.
Oh, I understand.
So it doesn't actually need to transfer anything through the tether. The tether is very flexible and thin. It couldn't actually transmit any force through it.
Okay, that makes sense. Thank you.
We'd all like to be able to get self-drilling nails for home improvement projects.
Hello. Is there ever a situation where a rover would be planned that would assist a previous rover? Is there anything that you could think of that would make that an opportunity that you would go for?
Yeah, I think it'd be totally cool if we could go send a rover and nudge another one. Right now, where the rovers are landed, they're thousands of kilometers apart. So, our current rovers to get from one to another would take Mars record, world record amounts of driving in order to do it. But in the future, we are thinking about, are there ways we might want to design groups of rovers that might go to a single site? How might that enable exploration? What would be the ideal number? And so these are all things we think about for future exploration.
Thank you.
And Abby, let me follow that question up because you helped to select the landing site for 2020, right? Or you worked.
I was part of the science community who provided
right,
input.
okay.
Yeah.
So one of the sites that was being considered was Gale Crater, right?
Yeah, so one of the sites was actually Gusev Crater. So one of the areas we thought about landing the 2020 rover was in Gusev Crater, which is where the Spirit rover landed. And that's because Spirit discovered some kind of interesting features that we thought maybe was a sign of past life. But maybe they weren't a sign of past life. And Mars is a big planet with lots to explore. So in the end, we decided the science rationale was just so much more compelling to go to Jezero. But there's interesting stuff at these sites we've been to, so don't rule out a mission in the future to go back there. I think that'd be pretty cool.
Thank you.
The last one. How hard of rock does the HP3 hammer be able to dig down? Have you been able to saw it through something like granite?
No, it actually can't go through rock at all. So if we hit a rock dead on, then we will be stopped by the rock. It can't go through it. However, if we hit a rock a little bit edge on, it can actually kind of start going a little bit sideways, and we can actually measure the tilt of the HP cube so we can see how deep it is even if it's going a little bit sideways. So it might be able to slip around a rock completely or go off a little bit sideways and keep going. If we hit a flat rock essentially dead on, then unfortunately we couldn't get through that.
Thank you.
I want to ask about the solar energy versus nuclear. we started the first landing on Mars with solar. And then we went into nuclear and went back to solar. There was some nuclear, okay. And now if solar had the problem that you have to clean, why didn't you use nuclear? And I see Bill here, who is the one who can answer that question too.
Well, I'll say for insight, we didn't need nuclear. Solar was going to work just fine. We landed within 4 degrees of the equator, so we're very close to the equator. And luckily, we just happened to be slightly tilted south, which is the perfect tilt for us. We oversized our solar arrays so we could make sure we could survive 1 full Martian year, including through the winter. And the good thing is, if you can survive 1 Martian year, there's nothing that says you can't survive the next Martian year. So there's always opportunities for the future. But we didn't need to go to nuclear to make the mission work, so we were able to do it with solar.
Yeah, but what about the dust?
There's the dust that we will always keep an eye on. If there's a dust event, then we know that we'll get dust in the arrays, but we oversize them knowing that that was likely to happen, and then that we'd get some dust cleaning events.
Are you going to go again with nuclear?
Yeah, so again, this all goes back to what's the requirement of the mission? You know, what science do we need to do? And that it drives how long does it need to last and how much power do we need? So nuclear is going to be a lot more expensive, more complicated, and it'll get you more power though. So for Spirit and Opportunity, we used solar panels because in terms of the power and how long we thought we needed to do the science to do, that was sufficient. For Curiosity and for Mars 2020, we're using nuclear because those vehicles just require so much more power. It would be impossible to size a solar array that would be big enough. So, you know, what's the mission that you want to do? How much power do you need? How long does it need to last? That's going to tell you what power source you want to use. And remember, it's all trade-offs in terms of cost and complexity.
Okay, thank you.
Well, I'll give folks another chance if anybody else has a question. I'll ask you guys if you want to get a little sciencey about that heat probe measurement. What do you learn from taking the temperature of Mars at these different levels? I mean, why do you want to know the temperature at multiple levels? What does it tell you about Mars?
So one of the things we want to measure is actually as the seasons come about on Mars, it heats the ground, and you actually have a heat pulse that goes into the ground. You want to see how deep that heat pulse can go, and also you need to be able to remove that from your total calculations of how much heat is flowing out of Mars. So you actually want the measurements at lots of different points. Also, we don't know how deep we'll actually make it into the surface of Mars. So we'd hate to have the heat probe sensor be at the very end of the tether and that be the one sensor sticking out at the top of the surface and the rest of the probe be underneath. That would just be terrible. So you want sensors along the way to make sure as you go down, you get some sensors into the ground.
Yeah, and I can just add, kind of from a geophysics perspective, when all rocky planets form, they have some residual heat on their core, and that heat is from just the energy from the planet forming and accreting, and also any radioactive elements that may be trapped down there are going to decay and they're going to warm up. And that heat on Earth, that's what drives the convection, that's what drives plate tectonics, that's why we have earthquakes and volcanoes. So the question is, a planet as small as Mars, you know, how much heat did it initially have? How did the heat cool over time? How much heat is it producing now? And you need that number in order to make these models to kind of backtrack through time.
And we could do models for lots of different variations, but this measurement will help nail down the models and say, you've got to at least match this point to be considered at least feasible.
Great. I know in December of last year, there was a beautiful picture release of this ice crater on Mars that was discovered. I'm not sure if that was by JPL or not, but what are the scientific implications of that discovery, according to you guys?
I actually missed that story when it went by, so.
I don't know a ton about it. I saw a little bit of the news story.
The Mars Express image, I think, right?
Yeah, I think so. And I mean, we know there's water on Mars. There's water at the poles of Mars, so it actually has ice caps that are permanent and also that freeze the atmosphere actually onto the ice caps. Think in Earth in the wintertime, if our atmosphere actually froze to ice at the poles, which would be really unique, that actually happens on Mars. So we know there's water ice and CO2 ice on Mars. The fact that in a crater that perhaps is shadowed a lot of the year, you could still have some sort of ice permanently there, or at least some for some point of the year there, doesn't surprise me. I don't know where on Mars that crater was, so I don't know exactly how surprised to be.
Gotcha. All right, thank you.
Cool. Hi there.
So you said with Curiosity, the rocks that you kept trying to drill into were too hard. Isn't finding a softer rock change what you're going to find once you drill into it?
Maybe.
Okay.
Yeah, but getting any rock sample is better than getting none. And we can do things. We can measure the chemistry and kind of the properties, and can see the chemistry is kind of in family with what we've been looking at. Does that mean that the minerals are the same? Does it mean that the little bits in it are the same? We'll never know. But getting one sample is better than no samples.
Thanks.
Hi, can you go a little bit more into the details about what we can expect to learn from the wobble of Mars? So are we looking at different densities and trying to figure out like a density gradient through the planet, or what exactly is it we're looking
In
at?
particular, the size of the core. So just like with the hard-boiled egg example, if you spin the hard-boiled egg versus one that hasn't been, it's going to wobble slightly differently. We're looking for how Mars wobbles over time. And with the sensitivity that we're going to get from this experiment, we can see not only the big wobbles it's going to do, but the tiny little wobbles on top of that. So we have measurements of the big wobble from 20 years ago from previous missions, and even 20 years before that, when we go all the way back to things like Viking. You can go back far enough that we have a few data points. InSight will give us another data point, and then in particular, high resolution of these itty-bitty wobbles on top of it. From that, you can constrain the models that say how much Mars should wobble depending on how big its core is, and a little bit what it's made out of on the inside.
Are you hoping to see any kind of evolution in like all the measurements we've taken in the last 20 years, or is that just too small of a geological timescale to?
We'll be able to see the difference in the big precession, essentially, of Mars's spin axis, but in terms of the little things, the InSight's the only one that'll have the fidelity to see that. So we wouldn't be able to compare that with previous missions, but the big position of where is Mars' axis tilted, this longer time span of about 40 years gives us actually enough time to look at a small change.
Thank you.
With InSight, are you going to be able to compare Mars to Earth in terms of whether or not it has a molten core, or how large it is, and what other features of comparison, like the magnetic poles and things like that?
Yeah, that's actually the goal of InSight, is to understand better this terrestrial evolution of planets. We've got the data for Earth. We've got the data for the Moon, which was formed a little bit differently, and it's small enough that it didn't have the same exact processes. We really want to see this data for Mars to see the intermediate mix of a planet that never had plate tectonics. So actually, we think its current structure locks in what it looked like when it finished forming, like 4 billion years ago. We want to understand, does it have a solid core or not? How big is that core? We have about a big variation in it. We want to get it down about a factor of 4 better than we know right now. How big is that core exactly? How thick is the crust? How does that vary? All those answers are what InSight's trying to look at, is that interior structure that we can't see from the surface.
Do we already know that it has a molten core?
We think it does, but it's still uncertain. So that's what InSight's actually trying to look at.
Okay. And given some theories that the moon was actually crashed into the Earth and then separated into 2 bodies, do we think anything like that ever happened at Mars?
We know Mars has had some really big impacts. Of course, we can see the craters on the surface of Mars. Mars's moons, we don't think formed in the same way as Earth's moon. They're much smaller. They look like kind of captured asteroid type things. But Mars, of course, has had impacts over the life of its formation. Whether it had a big one early in its formation, that's a little bit harder to tell.
So yeah, I love Mars's moons because they're super weird, and we super don't know how they're there. And there's 2 schools of thought that the asteroids, they really, from a distance, they look just like asteroids. But then it turns out dynamically it's hard to get asteroids and capture them and get them into the orbit that we see Mars's moons in. And it's a lot easier to form them if you have a big impact. And we're actually sending, JAXA is sending a mission to Phobos, which is one of the moons of Mars, and there's going to be a US instrument on there that's going to land, pick up a sample, and bring it back. And hopefully those analyses will tell us, is it Chunko Mars? It might be an impact from Mars. Is it like the meteorites we see? It might be an asteroid. So we're going to kind of solve one of these big solar system questions about what's the deal with Mars's moons.
Okay, thank you.
Hi. For the InSight craft, we talked about the seismometer and the mole. There are other instruments on that vehicle. Could you talk about some of the science that you're planning for those instruments?
Yeah.
Or are they just support?
Yeah, it's a combination. They both are supportive and they can do their own science. We call it stealth science. So we have the pressure sensor that can measure the pressure, the atmospheric pressure. We've got twins, which measures the wind and the temperature of the atmosphere. So between those, we're looking at things like how does the atmosphere behave? We can do very high precision measurements of the atmosphere, what its little local eddies look like. Is there dust devils coming through? How often do they happen? We've got the magnetometer looking at what's the inherent magnetic field at Mars, which is very, very weak, but we're trying to look for that. So we've got those three instruments supporting the seismometer and the heat probe as well as our RISE instrument looking at the rotational precession.
Thank you. And are there any cameras that you're going to be using for science or just support?
We do use some of the cameras for science. So we had to do a lot of the camera work for our workspace imaging, but the geologists love looking at the dirt and the rocks really close up. And of course, we're going to do some more panoramas looking around the lander to see more of the geology in the area, watching. Actually, one of the things we're trying to do is watch a little pile of dirt that happened when we dropped the tether to the ground. And there's a little pile of dirt that happened. We want to see, are the little grains of that pile of dirt moving and how fast based on the wind that's blowing in the area.
Thank you.
Hi, just a couple questions actually. It seemed as though in one of the slides for the upcoming mission in 2020 that in lowering the lander, there seemed to be another craft, if you will, with boosters to help it land softly. What is the objective with that other craft, if you will, whether to fly away or is there hope, if possible, to utilize that craft later on?
Yeah, so that craft is called the Sky Crane, and that is actually the same landing system that we used for Curiosity. So how it's going to work is it's can be coming through the atmosphere. We'll do the parachute. We'll slow it down. We'll deploy the back shell, and then we'll lower it on the bridle from the Sky Crane. And what happens is the thrusters on the Sky Crane will slow it down enough that we can touch very gently on the ground. You can't put thrusters on a rover because you need wheels. Where are you going to put the thrusters? So we'll deploy it, but then after that we're going to cut the tether and then send the Sky Crane as far away as possible because you don't want it to land on the vehicle. And in fact, a fun story from Curiosity's landing is one of the first pictures we took. There's like a little smudge off in the distance, and it could be dirt on the lens, but it's kind of pointed in the direction the Sky Crane went. And we know there was a lot of extra hydrazine on the Sky Crane, so it might be a bit of an explosion from when it landed. But we want to get it as far away as fast as possible from the vehicle because the vehicle is the main important thing.
I guess I was just wondering if you guys wanted to utilize it later on to maybe collect those rock samples, if possible, to get another thing. But the second question is, what makes a team decide to land a rover in an area that seems to might have water in the past versus going somewhere closer to where you feel is the water, like the ice caps, or somewhere close to the ice caps, things like that?
Yeah, that's a really good question, and it's a bit of a complicated answer, but there's kind of two main drivers. The first thing is, even though the 2020 rover will be nuclear powered, there still are restrictions on how far north or south you can go, because as you go closer to the poles, the temperature variations become very great, and you need to spend just so much energy heating the rover that it makes it hard. So you restrict it to a latitude range. And then you also start to get into interesting questions about planetary protection, which is a phrase we use a lot, and it means both kind of protecting our planet from samples we bring back in case there's any killer bugs, but also protecting the planet we land on from any forward contamination. And it turns out requirements near areas where you might have liquid water are really, really strict. So it makes it difficult to land there. You want to make sure your mission's really, really clean. And we think there's a lot of really good science to do in the sites that we picked. And the idea is, if Mars had life in the past, maybe the old rocks would be a great place to look.
Thank you.
I have a chemistry question for you. So you mentioned that Curiosity is the chemist that analyzes for certain organic compounds in the soil. I'm just wondering, how does it determine the structure of these compounds? Does it use mass spectroscopy or NMR or something similar?
Yeah, so it has an instrument called SAM, which stands for Sample Analysis at Mars. We like our 3-letter acronyms. And SAM is a gas chromatograph and a mass spectrometer on it. It's a quadruple mass spectrometer. And so what we do is we take the sample and we actually bake it in an oven, which is part of the reason it's so energy intensive, is because we heat the sample up to hundreds of degrees centigrade, and then we can measure the masses of the gases coming off.
Thank you.
I have a pretty simple question about the dust storm, but the question about the sky crane prompted me to want to share just a personal observation. Watching that landing and having read about it in the lead up to it, and then watching you all in the, in the control room and your reaction and everything was so exciting. I mean, to the point where in the career that I was in, I was a lawyer, and I watched this and thought, first of all, the whole Rube Goldberg, just whoever came up with the idea to pull off that landing blew my mind. But then to do it successfully and to see the joy and the satisfaction and the accomplishment in the room, I looked at it and I said, there was nothing that was ever going to happen in my career that would ever give me that kind of satisfaction and joy, and I left that career. And I'm much happier. So thank you. The question is, what causes a dust storm of that magnitude, a planet-wide dust storm on Mars, where the atmosphere is relatively thin, compared to Earth? And what would precipitate it specifically to happen at that time? Is this something that's connected to solar wind or just the atmosphere on Mars itself, other processes? Do we know?
If you know, just let us know.
So there are meteoriticists who study this sort of process on Mars, and we do know about these global dust storms as they start in summertime, when you have kind of warmer ground and you start to have kind of these differences in the temperatures, and you have these what start to become active lifting centers of dust. So it's not one big giant dust storm. What it turns out is you actually have a couple of these active lifting centers that start to lift. And so for this most recent one, we saw them pop up kind of around Acidalia planitia, and part of the reason it was so bad for Opportunity is there was one of these active centers that was like right next door to Opportunity rather than, part way around the planet. And you have them start to lift, and if you have enough of them and they become big enough, they kind of interact with stuff in the southern hemisphere, and that's when it starts to get bad and really mix up, and there's a whole bunch of dust that's kind of sitting in this big basin called Hellas Basin, which is one of these giant impacts. And kind of when you start to get that interacting with each other and picking up the dust that's sitting down there, that's when things just kind of cycle in on itself and it becomes this huge planetary encircling event. And this is a known phenomenon. We know dust storms have been going on. Every couple of Mars years, we get global dust storms. It's not a surprise, but it's a really interesting phenomenon. And some of the measurements that Curiosity made were really cool. Looking at how the temperature changes during the dust storm, we found that the seasonal differences dropped by many tens of degrees. Sorry, the diurnal differences, so that the nights were warmer and the days were cooler. We could measure how it actually affected the relative humidity. We can look at how it affects the pressure. When you have different temperatures, your pressure is going to change. So there's all these really neat kind of interlocking systems that happen that we were able to kind of get a good measurement on from the ground.
But being able to predict year to year, we know when dust storm season is, being able to say if a dust storm is going to happen, that's where we're not quite at yet.
It's one of the mysteries of Mars.
All right, any other questions tonight? If not, I guess we'll stop there. Thanks to all of our speakers. And thank you very much to all of you for being here and for watching us. Join us for next month's show when we'll focus on the world of scientific ballooning. So we'll see you then. Good night.